Hello student. In the previous lecture we discussed about the partial derivative and we also solved one problem related to partial derivative of function of two variables. Now today we will start with one more example and will find the partial derivative of function of two variables at the given point. So example is that compute the partial derivative of fx and fy at point at origin, that is 0 0, of the following function. So function is given like this, defined like this: fxy is equal to, this is equal to xy upon x square plus y square when xy is not equal to 0 and its value is equal to 0 when xy is equal to 0. So solution: so here we have the function fxy is equal to this one. So first of all we will find the partial derivative of fx at point 0 comma 0, and we know that it is evaluated by the formula limit s tends to 0 f 0 plus s, that is h comma 0 minus f 0 0 upon h. Now the question is that what will be the function f h comma 0, h comma 0, h comma 0, because fxy is defined like this: xy is not equal to 0. When both are not equal to 0, then it is behave like by this rule. We can find the value of fxy by this rule. But when both x and y are equal to 0, then it's f of x xy is equal to 0. So here both h and 0 are not equal to 0. This one is equal to 0, but h is not equal to 0. H is very small quantity which tends to 0. That means we will put in place of x here h, and in place of y we will put 0. Similarly here in place of h x square we will use h square, and in place of y square we will use 0. So it becomes h into 0 upon 0 h square plus 0 square. So ultimately it gives us the value 0. So f as 0 is a 0 function. So it is 0 minus f 0 0, value is 0, so it is again 0. 0 minus h is 0. So the limit of this function will be 0. So partial derivative of f with respect to x at point 0 comma 0 is 0. Similarly we can find here, similarly fy comma 0 0 is obtained by taking limit k tends to 0 f 0 comma k minus f 0 0 upon h. So f 0 comma k is again obtained by taking x is equal to 0 and taking k y is equal to k in the function fxy is equal to xy upon x square plus y square. So here if we put x is equal to 0 and y is equal to k, we get 0 comma k is equal to 0. So this gives us 0, limit k tends to 0, k tends to 0, 0 minus 0 upon h. So after solving this, we get this is equal to 0. So this implies that the both partial derivative fx and fy both are exist and equal. Both are exist and equal. But the one important note here, we can see that the partial derivative of the above function both are exist, but function is not continuous, even though fxy is not continuous. We know in case of one variable, in case of one variable we know that if f is differentiable, then this implies that f is continuous. But here we can see that fx and fy, that is partial derivative of function of two variables, both exist, but function is not continuous. We can check its discontinuity by taking the limit y is equal to mx. Then if we take y is equal to mx, then we get the limit x comma y tends to 0 0, f of xy is equal to limit x tends to 0, xy tends to 0 0. This is xy, fxy is xy upon x square plus y square. Now in place of y we will put mx, so it gives us limit x tends to 0. In place of y we will use mx, so it is mx square upon 1 plus m square into x square. So we can cancel out this s square by x square, so it becomes limit x tends to 0, m upon 1 plus m square. Since this limit depends on the value of m, depends on value of small m, so that means the limit of function of two variable is not unique along different path, or we can say the limit of function is different along different path. So this implies that the limit xy tends to 0 0, f of xy does not exist, and this implies fxy is not continuous, at origin. That means the existence of partial derivative of fxy does not imply the existence of partial derivative does not imply the continuity of fxy. And if f is continuous, this does not imply that f of x, that is partial derivative of x and y, exists. So but we can say, but if fx and fy both exist at point P,